I just left that out. If you have any question about that part, you ask me separately. Okay. So now, what is long run? What is very long run? Not long run. Very long run. You remember this graph I showed you in the beginning of this course? So this the reality of how economies are growing over time. So economies are growing along an upward sloping, hopefully, of course, path, but not in a very smooth way. Okay, so economies are fluctuating around this trend, long-run trend. Okay, so I started this course by breaking down this reality in two pieces. This piece, which is representing short run, long run. So long run is this. The economy is absolutely, remember in long run, capital fixed, labor fixed, output fixed. Okay? Full employment output is fixed. So this is long run, and short run we just finished is representing when economy can go above full employment, below full employment. Remember, in long run model, output cannot be different from Y bar, and Y bar was fixed. Okay, so that was long run. So short run, I just finished that. We can allow output, actual output, going up or above or below full employment. So this is what we finished, short run, long run. There was one little problem with this, okay? Not problem, from a modeling point of view, because modeling means simplification, okay? Just focus on the question. So I broke it down, this to this plus this. So because factors which are affecting the trend are different from the factors that they create fluctuations, okay? So we spent almost a big chunk of this course on short run, long run. Now we are going to talk about just long run, very long run alone, okay? So from here, whenever I talk about output, I don't mean output, I mean output capacity. How output capacity is changing. That is yet I artificially kept it fixed. It's not fixed because capital is changing, labor is changing, technology is changing. Is that right? So that would change what? The trend. Of course, here simplification is what? No fluctuations. No fluctuations. Okay? So from here, so very long run, capital is changing, labor is changing, therefore, and also something that I forgot, technology is changing. Possibly I missed the most important one. Okay? You remember in short run and long run, we kept technology fixed, labor fixed, capital fixed. Now everything is variable. Okay. Number two, you remember guys, in long run, nominal variables are not important because they are affected by only money supply. Money supply is neutral in long run, let alone very long run. Therefore, as you can see, I set aside money supply, I set aside price level. Can you see that? So you remember classical dichotomy? So very long run is focused on real side of economy. Because nominal side of economy, nominal variables don't matter from welfare point of view. So we focus on actual expansion of the economy, okay? So guys, no nominal variable, okay? Okay, let me tell you this. If you like this one alone, you can take a course called growth theory. Growth theory. Growth theory. So economic growth theory. So economic growth theory is just focused on this part. So they are talking about something, I don't know, depending on the level of the course, something like 15, 20 different models. Okay. In this course, we talk about 3, 4 models. Okay. So how do we get that many models? You see, if you change the assumptions and you can get a new model. Okay? For example, here I am going to assume that, and by the way, this is the first model. This is the first model in modern economics that we are going to discuss. Okay? So the first model, for example, as you will see, I am going to assume that there is no government, no G, no T. So you can add G and T, and then you get what? Kind of very complicated model. Okay, can you see that? So when you change the assumptions, you get a new model. The first model that I am going to present is the first model, by the way, Nobel Prize winning model, so-called solo model, as if you heard about the name of that. Okay, so guys, I told you, no fluctuations. So here I assume that economy is always at full employment. Unemployment is equal to national rate of unemployment, and output is always equal to 2.1. Don't forget that. Now, starting now, I am going to talk about output continuously, but I mean output capacity. I am not repeating that, okay? So that's easier. Traditionally, when we talk about growth theory, we are comparing growth path of different economies and compare them. But the problem is, yes?
What does N and L mean?
Oh, N is employment, L is labor. We assume that all employment is equal to labor, okay, full employment. You see, I said that in this area we are comparing different countries in terms of growth pattern. But you know, when you are comparing different economies, you have a problem. The problem is different economies have different sizes, and they are not directly comparable. For example, if you want to compare China with Denmark, Denmark is so small, okay? I mean, you barely can find Denmark on the map, okay? How can we compare Denmark and China? So that's why in this area, traditionally, we change everything per capita, per person, okay? So that makes more sense, okay? And the other thing here is, in models like this, in economic models, guys, in economic models, we never get population in the model. That's why instead of population, instead of number of people, we use labor force, workers, okay? Don't forget that. So whenever we say per labor, per worker, we mean per capita. Is that right? Because labor is a good proxy for population, okay? Okay, so let me tell you the story, how this thing started. Remember I said modern economics. Modern economics is the economics that you are studying in university. It is called neoclassical economics. No, I don't know if they told you. I mean, the school of economics that you are learning is called neoclassical economics. The problem with neoclassical economics in 19th century was neoclassical economics was overwhelmed by the idea of efficiency. Okay, you remember microeconomics? Okay, optimizations, perfect resource allocation. Okay, so they never talked about economic expansion, macroeconomic economic expansion. Never. So for, not never, I mean for 100 years. Okay, so since creation of neoclassical economics until 50s, like mid 19th century to mid 20th century, nobody in neoclassical economics, the one that you are studying, nobody talked about total economic growth. In fact, when I was a student, like your age, you know what happened? There was this part, very long run, didn't exist as part of macro. My time, remember I told you, my time there was no open economy. There was no long run, there was no very long run, there was only short run. That was, we called macro, okay? But now we have what? Short run, long run. Very long run, by the way, my PhD dissertation is in this area. I love this part, okay? But amazingly, this didn't exist in macroeconomics during my time. So I took this course separately as growth theory. It had nothing to do with the macro, but now they call it part of third horizon of the macro. So my point, for 100 years, neoclassical view was not even talking about economic growth until mid 19th century. A guy called Solow, he built the first growth model in economics, and that's why this model is a Nobel Prize winning. He won Nobel Prize in economics simply because he developed what? First growth theory in economics. Okay, so you see the idea went back to the time that some economists observed a phenomenon that was kind of shocking. What was that phenomenon? Phenomenon was this. Of course, this is a recreation. It goes back to mid 20th century. It looked like lower income countries are growing faster than richer countries. So what does that mean? If lower income countries are growing faster than higher income countries, so it means it's just a matter of time that they catch up. Is that right? You see, that makes sense. By the way, in that time, that idea was shocking. Wow, big idea. Oh, that's why some people came up with the idea of convergence theory. They said, okay, guys, we are going to converge. That was shocking because, it means what? It means sooner or later, everybody looks the same. Is that right? From prosperity point of view. So that's why people started doing empirical studies to see if this is right. Okay, for example, this is, of course, reproduction of study among OECD countries. OECD countries is a kind of a club of rich countries. Okay, so you see here? So here I have real per person GDP in 1960, and here, vertical axis, I have average annual growth rate of real GDP per person for 40 years. 40 years average is a very big long-term trend, is that right? It's not for 1 year, 2 years, 5 years. 40 years average is pretty stable, long run. So, did you see that? Relationship is negative. What does that mean? So, among OECD countries, Portugal used to be the lowest income country. But look at that, lowest income country, but fastest growth. Fastest growth for 40 years. Okay, and on the other hand, look at that, the rich countries, Sweden, US, Switzerland. So as you can see, richest countries, but they grew the slowest. And when this shocking thing happened, people started applying the same experiment everywhere. For example, this is a famous study, shows convergence among states of the United States. Can you see here? So 50 states. So personal income per capita, so something like a real GDP per capita. 1982, 1 year to show how rich and poor those states are versus what? Average, this is very interesting. Average growth rate of GDP per capita for 120 years. 120 years average is very stable long-term number, growth rate. So as you can see, it is heavily negative. So they applied these ideas in many places, like European countries, Japanese provinces, many places. Okay, so they got more or less the same result. Until they did this. Imagine. So they put together, not specific countries or places, they try to put together as many as countries that they can. They have information. So you see, as soon as they did that, all of a sudden, the theory crashed. Did you see that? So in fact, can you see that? So it looks like, in fact, a little bit positive correlation, that the negative correlation just disappeared. The negative correlation just disappeared. In fact, statistically, remember from statistics, correlation is not significant. Significant means correlation is zero. Okay, zero for a little bit positive. But essentially, it looks like there is no correlation. So the issue was, what happened? So what happened to this relation? So that's why this theory, that now we call it absolute convergence theory, that all countries are converging to the same point, is not working. Okay. So why? So what happened with these guys? So as you know, in statistics, they talked about sampling bias. So from a statistical point of view, they said these samples had sampling bias. Why? Because some OECD countries are not random countries. They are the sample of countries that converged. So when you sample, if you choose only converged countries, so of course you get convergence, okay, or states of United States. It's not a random sample of countries. So if you choose countries randomly, or you choose all countries, so there is no correlation. Okay, so that idea went out of the window. However, after that, some economists changed that to conditional convergence theory that they are following now. Okay, so in fact, two of my professors are two major brains behind this theory, conditional convergence theory. Okay, so I was writing, they were my supervisor too, okay, so PhD dissertation, but I personally don't like convergence theory, okay, that's personal, okay? So that's why we had to divorce each other, okay, so I changed my supervisors, okay, but anyway, it's a very big deal now. Okay, so let's see. For now, guys, forget about convergence. When I create my model, I come back and you can understand what's going on here better. Is that right? So don't worry about that. My point here is that has been the tradition starting growth theory, and as you will see, whatever model that we make these days, what do? We check convergence. Okay, but what is exactly convergence, and what we mean by absolute convergence, conditional convergence would be when we finish the model. Okay, so guys, solo. So we are going to build first model in classical view about growth theory, and talk about what? A Nobel Prize winning model. So you see, I am going to make his model, I am going to introduce 5 things, some of them from micro, some of them from macro. Okay? So we combine these 5 things and then we construct first growth model. Okay? Number 1, production function. And you know that. This is purely micro concept. So remember, in microeconomics, we assume that each company has a production function. What is production function? Production function is a technical function, relates to amount of inputs to total amount of output that you can make, maximum amount of output that you can make. That's the definition of production function. It's linking inputs to maximum amount of output that you can produce. Okay, production function. Now, you remember microeconomics? And also, you remember we talked about this in chapter 3. You remember that chapter 3? So, production function. So output, real output, be careful. I told you, that's the last time I am reminding you. Whenever I talk about output in this part, I mean output capacity by bar, full employment output. Okay? So we assume that there is only one type of labor force, and there is only one type of capital. Okay? And F function is representing the production function. Production function, which is representing technology, nature of technology. Okay? Remember I told you if you take a course in growth theory, you end up with, I don't know, 15, 20 different models. I told you, for example, there are models that they assume that we have different kinds of labor force. For example, we may touch about a model in future that we assume that we have two kinds of labor force. Labor force who are producing goods, labor force which are producing knowledge, okay? So science, okay? Or maybe different forms of capital. So here I am assuming that only one kind of capital, like physical capital, but there is a model that we have two kinds of capital, human capital, physical capital. Can you see that? So when you change assumptions, you change the model. Okay, this is the first model. Remember in chapter 3, we talked about different technologies behind production function, you remember that? So in macro level, we assume two things. We used that before, constant returns to scale technology. So you remember in macro, they talk about decreasing, increasing, constant return to scale technologies. But in macro, as I discussed in chapter 3, constant return to scale is more reasonable. Okay, so you remember what it meant? So if I multiply all inputs by any factor except 0, so output will be multiplied by the same factor. Okay, and also the law of diminishing returns. We have that in macroeconomics. So the law of diminishing returns to capital, diminishing returns to labor. You remember, chapter 3, we had the definition of that. So the diminishing returns to capital means what? You keep labor fixed, you increase capital 1 unit at a time, output does go up, but in diminishing way. You remember chapter 3? Okay, so how do I use constant return to scale here? So, okay, you remember gamma, sorry, this is not gamma, this is lambda. Lambda can be any number except 0. We can multiply everything by 2, by half, okay? So in this case, I am going to choose lambda 1 over L, okay? Then what happens? So you see, so it would be y over L, k over L, L over L would be 1. Yes, everyone? Okay, so you have this. Now, what is this? Y over L. So see, Y over L is per labor, per worker output. Remember, I am using this as per capita. Remember, in this part, we want everything per capita. But finding things per capita is very hard here in this case. So for us, per labor, per worker would be the same. So guys, I'm talking about final exam. If we talked about population growth rate, anything about population, we mean labor force. Is that right? Because labor force is assumed to be a proxy for population. So per worker output and per worker capital. That is it here? So constant return to scale from mathematical point of view helps me to define production function in terms of what? Per worker everything. Per worker output as a function of per worker capital. Okay, that is, of course I told you in the past, in macro, constant return to scale is more reasonable because you can always copy a factory in a different city. So capital doubled, labor doubled, output will be doubled. Okay, but it helps us mathematically to define everything per capital. Okay, so how am I going to use diminishing return? So, see, this is how I am going to use it. I am going to use diminishing return to capital. So if diminishing return to capital is right, remember, I keep labor fixed and I increase capital 1 unit at a time. Is that right? What's the outcome of this? So you see, output does go up, but each time less than before. You see, this is the graphical presentation of diminishing returns to capital. So if I connect these points, so it means my production function. Okay, actually this is little y. So that is little y. So typo. You see? So it means what? How do I use the law of diminishing returns to capital? Graph. In future graphs, I always draw a graph concave. This concave shape. You see that? Is coming from the law of diminishing return. So production function is not convex, it's not linear. Okay? It's concave. Why? Diminishing returns. Okay? So this is the formula. This is the graph. This is how I use my assumptions. Now, how can we use the law of diminishing in practice? So, remember in chapter 3, I called this my favorite production function. I used this several times in the past, chapter 3. So, this is what you need to do in final exam. In final exam, if there is a question like this, where you have a production function, the first thing that you have to do, you have to change everything per capita, per worker, of course, okay? Okay, so how do we do it practically? Okay, so just divide both sides by L. Divide both sides by L, remember, per worker. So can I simplify this? L and L to power of 0.7. So it would be L to power of 0.3 denominator. Yeah, agree? So now K 0.3, L power of 0.3. Can I put them in like a bracket? Is that right? You see? Agree so far, guys? See here? But what is this? Capital Y over L is a little y per worker output. Per worker output, per worker capital. Can you see here? So this is the formula. This is the graph. Graph is concave. So guys, final exam, the first thing that you need to do. Then you get the production function, change everything per capita. This is the first thing that you need to do. Yeah? Okay. Okay. So is everybody okay here? This is my first thing that I want to do. Production function. And everything about production function. Step number 2. Step number 2, macro. It's coming from chapter 3. Remember in chapter 3 we talked about what? 2 approaches to find GDP. Remember GDP from expenditure side, GDP from income side. You remember that? Expenditure side, remember planned expenditure, and income side. So look at that. So these two must be equal. By the way, we did that. You see? So these two are equal. So left hand side, so right hand side must be equal. Right hand side is equal, consumption cancels out. So I have this. And you are familiar with this. Investment is equal to national saving. Remember? Private saving, public saving. Actually, I gave you a question in your midterm test about this. Okay? But suppose government doesn't exist. Government doesn't exist. So if government doesn't exist, public saving doesn't exist, so investment is equal to private saving. Is that right? That is second thing that I need. Okay. Okay. Third. So that was second thing that we needed. Third. So, in this model, Mr. Solo assumed that saving is a fixed fraction of output, fixed fraction of income. Fixed fraction of income. Can you see that? So this is called saving rate. Saving rate. So it means what? You remember we always wrote C y minus t. Is that right? You remember that? Since day one in this course. So there is no t. So consumption is a function of income. So if you assume this, so it means this function is like this. Remember, marginal probability to consume, S is marginal probability to save. Remember, marginal probability to consume plus marginal probability to save, they add up to 1. Remember that? So now I have an explicit function for consumption function. I didn't write this before. So, you see, this is my investment saving relation. This is my saving function. So if you apply here, so you are going to have this. So in this model, investment is equal to national saving, private saving. Remember, national saving is private saving is S, public saving is T minus G, 0. And saving is equal to fixed fraction of output, income. Okay? You know that. You remember 20 different models? So for example, one little model that you can get out of this is this. So you see here saving rate in this model is fixed number. But you know that saving is not a fixed number. Saving is a function of income. So you know that rich people saving rate is high or low. Rich people have higher saving rate or lower saving rate compared to poor people. You forgot? So you see, when people become richer, saving rate goes up. It's harder because as you get richer and richer, okay, how many more burger you want to eat? Is that right? Share of consumption shrinks. So in fact, S is a function of income. But here that. So if you make that S as a function of income, that little thing makes this Solo model one of the most complicated models. That in fact my PhD dissertation was just that. It's called the Ramsey model. Ramsey model is just, it comes out of Solo model, but just that change. So you need optimal control theory. Optimal control theory is advanced math. Okay, so but simple. So here you go. So this was number 2. This was number 3. So number 4. Remember I said capital is changing, labor is changing, technology is changing. Let's talk about capital. Capital is changing, but does anybody know how capital is changing? Guys, can you just advise me how capital changes? Capital stock. You will be assume that capital is fixed. Now suppose capital is changing. How does capital? How do we increase capital? Anyone? How do we increase capital? Capital stock. Is it investment? Is that right? You see, stock of capital of like Canada is all machines, things. Is that right? So investment means more capital. So you see, capital is changing by what? So capital is increasing by investment. How does capital go down? So when you use machines, buildings, what happens? Sorry? Depreciation. Is that right? Depreciation. So you invest new machinery, you are using them, So depreciation. So let me write here. Depreciation. And generally capital depreciation, we don't have complicated model for that. Okay, we assume that depreciation is proportional to the size of capital. For example, have you heard about that? Depreciation rate 10%. So is that right? So it means a fixed fraction of capital is depreciated every year. Okay, so depreciation rate 5%, 10%. You see, and let me tell you personal memory, it may help you too. Since I was a teenager, so I have been using this model, tank of water. And I use this everywhere, in engineering, in economics. It works everywhere, in medical science. So you know that some variables are stock variables, some variables are flow variables, okay? For example, here, I assume that I have a tank of water. See, suppose you have a tank of water. Total amount of water is stock variable. So how does it go up? So suppose you have a water tap, and suppose you have a drain. So water tap adds water to this, drain is reducing water. Is that right? You see, it works all the time. It works all the time. So the same thing here, you see? Your tank of water now, imagine, is capital stock. So investment is adding and depreciation is subtracting. Can you see that? It works all the time. It works all the time. So downtown, I am teaching environmental economics. So in environmental economics, we have this. So this is what? Total amount of pollution. Total amount of, suppose total stock of CO2, yeah? So total amount of CO2 is increasing by what? By increasing what we call emission over there, emission. So each year you emit more CO2, is that right? And then nature has mechanisms to reduce CO2. For example, you have forests, you have oceans, you know that oceans, forests, they absorb CO2. Can you see that? So you see, it works all the time. It works all the time. So in fact, the amount that nature can take out over in that course, you are using this, alpha times pollution. So can you see that? So alpha is the rate, we call it land decay rate. What percent of CO2 in air can be absorbed by air? So, see, this variable is stock variable. So these two variables are flow variables. Variables which are adding or deducting stock variable, they are called flow variables. So, you don't know how many different, I don't want to waste your time. We have cases like this I used in engineering, okay? So this is a very useful idea. This is a very useful idea. Now, so whenever we have a concept like that, so remember this part. Suppose I have a capital stock. Suppose inflow of capital is more than outflow of capital. What happens if inflow of capital is more than outflow of capital? What happens next? Or inflow of water, outflow of water. Inflow of pollution, outflow of pollution. So you see, if this is the case, capital stock goes up. Is that right? You see, if there is more inflow, so capital stock goes up. Is that right? Yes, everyone? So capital stock goes up, you see, it means delta K is positive. It means K goes up. People continuously confuse here. When delta K is positive, it means K goes up. Is that right? So what happens if outflow is more than inflow? If outflow is more than inflow, so it means change in capital is negative, that means capital stock is going down. Be careful. Change in capital is negative, but capital cannot become negative. Capital goes down. Okay, my next question. What if inflow of water and outflow of water, or inflow of capital and outflow of capital are equal? Then what happens? If inflow of capital and outflow of capital are equal, then what can we say? Sorry? Yeah, that means delta K is 0. So that means K is fixed. Is that right? See here? Actually, be careful. You may not believe that. I have seen students in the past, you see, delta K is 0. Some people say, oh, K is 0. Delta K is 0. It means K is fixed. K is fixed. Is that right? Now, this case is very important because we call that what? That is my, you remember, guys? This is a very long run. You remember, I talked about short run equilibrium, I talked about long run equilibrium. So if you ask me what is very long run equilibrium, this is very long run. This is very long run equilibrium. Actually, you can interpret this differently. Sometimes we call this steady state equilibrium. Steady state equilibrium. So in a few minutes, maybe next week, we are going to define that differently. Okay, guys, this is my capital accumulation. Number 4. Number 5. Remember, labor is variable. How does labor change? How does labor force change? Guys, for this question, you need to take a half course officially called population economics. So it's equivalent to this whole course, a half course, okay? But in order to get rid of that course, so Mr. Solo made one little assumption. He assumed that labor force is growing at rate n, exogenous, which is not, of course, correct, but you need that course. Okay, that is step number 5. Now, guys, today, just today, let me make life easier, not next week, just today for the remaining of the time. I am going to assume that n is 0. So it means labor force doesn't grow. Labor force doesn't grow. So LT is equal L, initial fixed number. Okay? Okay, guys, that was my 5 elements. So it's time to what? It's time to combine these 5 elements. Number 1, production function, everything per capita. Number 2, saving rate I is equal S. Number 3, saving function. Saving is a fixed fraction of output. I am just listing everything just to remind you. This is how capital stock is changing. Inflow of investment, outflow of investment. Inflow of capital, investment. Outflow of capital, depreciation. Number 5, labor force. Suppose just today labor force is equal to fixed number. Labor force is fixed. Okay, guys? Now, how am I supposed to combine these 5 things? Let me start by this. You see, let me combine 4 and 5. Okay, how? You see, L is a fixed number. So can I divide everything here by L? Yes, everyone? Yes? So, I divided everything by L. Okay, now look at here. What is this one? I. Can I write this S? Can I write this equal to S T? Is that right? Remember, in this model, saving and investment are equal. Is that right? Okay, I did that. So let me write one more thing, guys. Delta K over L, I can write it this way. I can here. So here I wrote S over L. Look, delta K over L can be written as delta K over L with one comment. You see, because L is a fixed number, you can do this. Change in K divided by L would be the same as change in K over L. This is not always true. It's true if L is a fixed number. If L is a function of t, which is next week, you cannot write this. This is wrong. That's a simplification to this. Okay? But when L is a fixed number, so change in K divided by L is the same as change in K over L. Okay, so you got that. And then look at here. S total saving is equal to S times Y. Alright? See, just plug it here. And also notice this. See, K over L is little k. K over L is little k. Okay? So let's write it here. Little k, little k, little k, little k. And here I put fixed fraction of output. And look at here. This one. What is this? It's little y. Big Y over L is little y. And little y. But little y itself is f of little k. That's it here. So this is little y. But little y itself is little f of little k. Guys, this is solo one. You got Nobel Prizes to do like this. Of course, for first time. First time is always important. Is that right? So you see, remember in this course we do everything intuitively, algebraically. We did intuition, algebra. Now we are going to analyze this graphically. But before we do it, let me bring two things into your attention. So number one, look at here. What is this? What is this equation? This equation is the same equation as equation number 4. You see, these two are the same thing. So it means solo model is representing capital accumulation with one difference. That is total capital, which is always true. This is in terms of everything per worker. Per worker, capital per worker. Understand? Everything per worker. So number 4 is capital accumulation, total capital, solo model per worker. Capital accumulation just in terms of per worker, per capita. That's it. That's point 1. Point 2, you remember? Investment is inflow of capital, depreciation is outflow of capital. You remember that? So, I told you, this is the same equation. Please note that. It doesn't look that way. But S times F of K is still investment inflow capital. Worker. Is that right? This one, per worker, inflow capital, this is representing per worker outflow capital. It's still the same thing. It looks different. So let me put it here. So now let's drop everything over there in form of graph. So per worker output, per worker capital. Per worker output, per worker capital structure. So let's focus on this. Inflow of capital. Remember I told you, it looks different, but it's still inflow of capital. But per worker. Per worker. Okay, how does that look like in the graph? You see? How does this look like in the graph? S times F of K. So, actually let's do it in 2 pieces. How does this look like? F of k. Is this production function? Remember I developed that concave thing? So I took your time, and remind you the law of diminishing returns for now. If I want to draw f of k, the law of diminishing return, so that look like what? Concave, is that right? Not convex, not linear. That is f of k. But in fact, I don't want that. I want s times f of k. Okay, but don't forget that saving rate is a number between 0 and 1. Remember, marginal probability to consume is a number between 0 and 1. So s and marginal probability to consume add up to 1. So what if I multiply that graph by a number between 0 and 1? How does that look like? It looks like the same, is that right? Just scale down. Yes, for example, suppose saving rate is 1/3, 50%. So how does S times F look like? 30% lower, is that right? So see, it looks like this. Agree? Agree, everyone? Any problem so far? Okay, that is inflow of capital. How about this? This part. Outflow of capital. So let me write it here. Now I want to draw this. I want to draw delta times k as a function of k, little k. Guys, can you help me with this? How does this look like? Delta k as a function of k, I mean in the little graph. So delta k here, so k here. Delta k looks like what? Anyone? Any? Yeah? Any suggestion? Left? Right? Delta k as a function of k looks like what? K is a fixed number, you remember that? A number between 0 and 1. Depreciation rate. Suppose the depreciation rate is 5%. Or any number. No suggestion? No? Is it a line? Yeah? It's linear. Okay, what kind of line? Is it like a positively sloped line? Yeah, positively sloped line. Positively sloped line, what is its slope? What is its slope? Delta. Yeah? You need one more thing. It's a line, positively sloped. As a matter of fact, the slope is delta. Still, one more important thing. Anyone? If I want to draw this versus k, so it would be what? It goes to the origin because it doesn't have intercept. Can you see that? If k is 0, delta k is 0. Can you see that? So 4 things. So here. Linear, positively sloped, it's not like this, it's not horizontal, it's not vertical, and its slope is depreciation rate, yes, and also it goes to the origin. Can you see that? So depreciation line, this is representing outflow of capital, the red line. And this green curve is representing inflow of capital. Yes? So now my next question. Imagine this point. Suppose my economy has this much capital. Let me call that K star. Suppose my economy is here. This much per worker capital. So can you tell me what's going on at that point? At that point, what's going on? So by an amazing accident, economy has this much capital, K star. No opinion? What can you say about inflow of capital, outflow of capital at that point? Inflow of capital, red line, outflow of capital, green line. So they are intersecting over there. So it means at that point, inflow of capital and outflow of capital are equal. But when you have inflow of capital, outflow of capital equal, so it means capital stock doesn't change. So it means K star is steady state equilibrium. Very long run equilibrium. You remember that? We talked about short run equilibrium in the past, long run equilibrium in the past. That point, not that point, this point, you see here? Point O. Point O is representing very long run equilibrium or steady state equilibrium. So it means if economy is at point O, it's going to stay at point O forever as long as you haven't changed anything. Because of this, because inflow of capital is equal to outflow of capital, capital stock doesn't change anymore, so your income, your capital per worker would be K star. If you plug it into production function, Y star would be your steady state equilibrium of your system. But I said if your economy is at point O by an amazing accident, it's going to stay there. So what if your economy is at point K1? Suppose amount of capital per worker is currently this one. You want the tank of water? Suppose tank of water has this much water. Anyone? What's going on? Suppose economy instead of K star has K1 water, amount of water. Is that right? Anyone? What's happening there? Look at here. At that point, look at here. What is inflow of capital? Inflow of capital is this much. Agree, everyone? Yes? Oh, sorry. Sorry. One more time. Yeah, so inflow of capital is larger than outflow of capital. So when inflow is larger than outflow, what happens? You remember inflow of water is more than outflow of water. Water goes up. Okay, goes up, capital goes up, so it means you are moving what direction? Right. See here? Yes, you guys are right. Look at here. So this much inflow of capital, this much is outflow of capital. So capital is going up. So it means we go this way. Do you see that? And we go this way. Yes? So inflow larger than outflow. So capital goes up, output goes up. So as you can see, if you are anywhere to the left of K star, you move towards K star. Okay? If you are anywhere, see, to the left. Okay, how about this one? Suppose your amount of capital is K2. So you see, K2. What is outflow of capital? This is outflow of capital. Agree, everyone? Yeah? What is inflow of capital? This much, yes? So you tell me, outflow of capital is more than inflow of capital. What happens to capital? Yeah, it goes down, so yeah, you're right. It goes to the left, okay? It goes to the left. So what do I learn here? So let me write it here. So anywhere to the right of steady state equilibrium, so output and capital are going down and you go towards K star. So what I learned here is this. So I am going to, this is what I learned. Point O is, it's not just steady state equilibrium, it's stable steady state equilibrium. It's stable steady state equilibrium. Yes? Stable steady state equilibrium. Is that right? Does this make sense? You see? So here we showed long, very long run steady state equilibrium and how we get there. Okay. Now, please look at that graph one more time because I want to ask you a question. I showed you point O myself as a steady state equilibrium. Prove that. Okay, it's stable steady. Okay. So in this graph, in this structure, there is another steady state equilibrium. Can you find that? Now, this time you find that for me. Point O is not the only steady state equilibrium. Anyone? Can you find it? There is another steady state equilibrium. What is the condition for a steady state equilibrium? Inflow must be equal to outflow. Yes. What? Okay, yeah, interval inflow and outflow, that was how I got point O. But there is another one. So, you mean here? No, so, which intercept then? Red line and green line? Oh, okay, yeah, this is how I found it. This is how I found it. But there is another one on top of that. Just follow the same logic. Yes. Origin. You see? After all, yes, you are right, intersection. But there are two intersections. This one that I found, and another one is this one. Of course, that is very boring steady state equilibrium because everything is zero. Is that right? Zero output, zero consumption, zero investment, zero savings, zero everything. So it means nothing. Is that right? Nothing. But my point here is something else. That's why I brought that up, because that is just a kind of very boring, useless. But what's the difference between, okay, yes. But what's the difference between A and O? You see, both of them are steady state equilibrium points. But there is a major difference between A and O. Of course, I know in A everything is zero. But forget about that. Something different. Very, very big difference between A and O. Both of them steady state equilibrium, but very big difference. Anybody noticing anything unusual at point A? No? Okay, let me give you a hint. Can you compare A and O in terms of stability, Yomer? Both of them are state equilibrium. But what can you say about stability? Yomer, for point O, I said if you go to the right, if you go to the left, this happens and this happens. Can you apply the same idea to point A? For example, yes. Sorry. Yeah, of course, when you are at point A, you cannot go to the left because you don't have negative. But my point here is, what if you can go a little bit to the right? How that? Suppose I go just 1 millimeter or any amount to the right. Yeah, so it goes where? So if I go a little bit to the right, oh, okay, well, where is the next point? Yeah? Yeah. You see, if you go even 1 millimeter to the right of point OA, you don't go back to A, you go to O. You see that? Point O is stable because if you go a little bit to the right, or not a little bit, a lot to the right, a lot to the left, you always go back to O. But not for A. Not for A. A, if you go just 1 millimeter to the right, look at here, why? Let me show you why. I want to make sure everybody can see that, you see? If you go, okay, let me make it a little bit more than a little to the right, okay, this much, okay? So if you go to the right, inflow of capital would be more than outflow. So it means you are moving this direction. This direction is what? O. So point A is unstable. So see guys, dynamic systems, first you have to find a steady state equilibrium. Number two, you need to find stable, if they are stable or unstable. Okay? Actually at point A, nothing is going on. It's like you are in the middle of desert, there are nothing. So I'm sorry for this, my example. I use the example of God. Suppose God drops 1 penny from the sky to this economy. What happens? You go to O. Okay, so okay, let me stop here. Practice this. Next week, I am going to remove that assumption. You ever assume that labor force doesn't grow? Okay, of course that's not a good idea. Suppose the growth rate of population or labor force is positive. Okay, then what happens? Then that model doesn't work anymore. So you need to change that model. So practice this easy version. Next week we are going to talk about more general case with population is. Okay, thank you guys for stopping by. I know Friday, summer, early morning. I really appreciate you are taking your time and come to class. Thank you very much.